Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. My name is Fadli bin Shahriar. Today I will talk about the second law of thermodynamics. In the previous chapter, we applied the first law of thermodynamics, or the conservation of energy principle, to processes involving closed and open system. The first law of the thermodynamics characterizes the balance of energy, which defines the quantity of the energy itself. But in the second law of thermodynamics, the law defines the direction which the process can take place and its quality. A process cannot happen unless it satisfies both the first and the second law of thermodynamics. It is common experience that a cup of hot coffee left in a cooler room eventually cools off, as shown in the top left figure. This process satisfies the first law of thermodynamics, since the amount of energy lost from the coffee is equal to the amount gained by the surrounding. Now, let us consider the reverse process. The hot coffee getting even hotter in a cooler room as a result of heat transfer from the room air or from the surrounding. We all know that this process never takes place, yet doing so will not violate the first law as long as the amount of energy lost by the air or the surrounding is equal to the amount gained by the coffee. As another familiar example, consider the heating of a room by the passage of electric current through a resistor, as shown in the bottom left figure. Again, the first law dictates that the amount of electric energy supplied to the resistant wires be equal to the amount of energy transferred to the surrounding. Now, let us attempt to reverse this process. It will come as no surprise that transferring some heat to the wires does not cause an equivalent amount of electric energy to be generated in the wires. Finally, consider a pedal wheel mechanism that is operated by the fall of mass in the last figure. The pedal wheel rotates as the mass falls and steers a fluid within an insulated container. As a result, the potential energy of the mass decreases and the internal energy of the fluid increases in accordance with the conservation of energy principle. However, the reverse process, raising the mass by transferring heat from the fluid to the pedal wheel, does not occur in nature, although doing so would not violate the first law of thermodynamics. So therefore, we can conclude here that these processes cannot occur even though they are not in violation of the first law. It is clear from these arguments that processes proceed in a certain direction and not in the reverse direction. In other words, process occur in one-way direction only. There have several examples of physical processes in nature can proceed toward equilibrium spontaneously. For example, here, water always flows downhill. This is what we call as one-way direction. And water cannot flow backward. Otherwise, we have a special device that can make or change the elevation of the water. Second example is these hot balloons. The gases inside the hot balloons always expand from high pressure to low pressure. So therefore, it makes the hot balloon move upward. And last but not least, during winter, we use a heater. We know that heat from the heater always flows from high temperature region to low temperature region, so that the room can be warmed up. Even though many processes in nature cannot be reversed, but we must know that the processes is actually can be reversed. In order to reverse the process, it requires the expenditure of work. And the term of this work is very, very important in this slide, because from work we can reverse the process. In the first law, it gives us no information about the direction in which a process occurs. It is only tells us that energy must balance. And we have learned the energy balance equation. But here, in the second law, it will tell us what direction processes can be occur. And this is what we are going to learn in this topic. As pointed out earlier, work can easily be converted to other forms of energy. But converting other forms of energy to work is not that easy. For example, in this figure, the mechanical work done by the shaft shown in this figure is first converted to the internal energy of the water, and this energy may then leave the water as heat, which means energy from the water is released to the surrounding in terms of heat. We know from the experience that any attempt to reverse this process will fail. For example, at the right side of this figure, we have heat from the surrounding, and we want to make the shaft rotate by using heat from the surrounding. And that is, transferring heat to the water does not cause the shaft to rotate. It is impossible. And from these and other observations, we conclude that work can be converted to heat directly and completely as shown in the left side figure, but converting heat to work as shown in the right side of this figure requires the use of some special devices, and these devices are called heat engines. So if we want to make the shaft to be rotated, by using heat from the surrounding, we have to use a special device that called heat engines. There are several major uses of the second law of thermodynamics. First, this second law may be used to identify the direction of the processes. Second, the second law also asserts that energy has quality as well as quantity. In the first law, it is concerned with the quantity of energy and the transformations of energy from one form to another with no regard to its quality. But in the second law, it provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. Last, the second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems, such as heat engines and refrigerators, as well as predicting the degree of completion of chemical reactions. Before we go further, we have to learn and know the concept of thermal energy reservoirs. And thermal energy reservoirs is a system that remains at constant temperature even though heat is added or removed from the system. For example, the atmosphere, it does not warm up as a result of heat losses from the residential buildings in winter. Likewise, megajoules of waste energy dumped in large rivers by power plants does not cause any significant change in water temperature. This is what we call as thermal energy reservoirs. Even though heat is added to the system or removed from the system, they don't have any significant change in temperature. And thermal energy reservoirs is categorized into two. The first one is source. Source means a reservoir that supply heat or can supply heat, while steam is a reservoir that receive or absorb the heat. Okay, now let's learn about heat engine, a special device that can be used to convert heat to work. I have listed several mechanisms of the heat engine. First, the heat engine will receive heat from a high temperature source. For example, solar energy, oil furnace, nuclear reactor, and so on. And here is what we call as a source. And this source will supply an amount of heat Q in to the heat engines here. This is heat engine. And the heat engine will convert part of this heat to work. And they will reject the remaining waste heat to a low temperature sink. For example, atmosphere or rivers. And this heat engine will operate on a cycle. Heat engines and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle, and this fluid is called the working fluid. This working fluid will absorb the heat from the source, convert into work, and release a part of the heat to the surrounding, to the environment. This is the concept of heat engine. One of the famous examples of heat engine is a steam power plant. In the steam power plant, they have four components. It starts from boiler. Boiler will receive heat from source. Then turbine will convert the heat into work out or work done. Then third component, condenser, is used to release heat to the atmosphere. The last component in the steam power plant is pump. Pump is used to bring the working fluid back to the boiler, and pump need W in order to operate. Q in this figure means that an amount of heat supplied to steam in boiler from a high temperature source. And Q out is an amount of heat rejected from steam in condenser to a low temperature sink, while W out is an amount of work delivered by steam as it expands in turbine. And last but not least, W in is an amount of work required to compress water to boiler pressure. Then, if we narrow down to the heat engine, we know that heat engine is used to generate or provide W out. And this W out, a portion of the work output or W out of a heat engine is used internally to maintain continuous operation, which is W. And this W net out is called as required desired output, the output that we need. And from this system, we can develop an equation of work. W net out is equal to the W net out is equal to W out minus W in. Or in other words, we can say W net out is the difference between work done on the system and work done on the system, which is W in. They have another equations here. which is W net out equal to Q in minus Q out. And this equation will be explained in the next slide. And it is actually come from the energy balance equation that we have learned in the first law of thermodynamics. Okay, next is thermal efficiency. The thermal efficiency is the index of performance of a work-producing device or a heat engine. Thermal efficiency is the index that will tell us the performance, the quality of the system. And this thermal efficiency is the ratio of the net work output to the heat input. And this net work output can be called as well as the desired result or desired output, while the heat input can be called as well as required input. So from this figure, we have a heat engine, a source, and a sink. This heat engine receives QH from the source, produce W net out, and release QL to the sink. From this schematic diagram, the thermal efficiency is W net out over QH. Okay, as I said just now, the thermal efficiency is the ratio of desired output to the required input. Again, from this schematic diagram, here is W net out. Here this W out is work done by the system. In order to determine the net work done, you have to find the difference between W out and W in. And this Q in is the required input. Most of the heat engines operate between a high temperature source and a low temperature sink, and the heat engines operate in a cycle. So therefore, the cyclic heat engines operate between high temperature source and low temperature sink. Okay, now let's apply the energy balance equation in the heat engine. We know that the energy balance equation is Q net in minus W net out equal to delta U plus delta KE and delta PE. Since the heat engine operates in a cycle, the delta U, delta KE and delta PE can be neglected or equal to 0. So now the energy balance equation for cyclic heat engine can be written as W net out equal to Q net in. And this Q net in is equal or similar with the difference of Q in and Q out. So now the energy balance equation for a cyclic heat engines is W net out equal to Q net in and equal to Q in minus Q out. Then for the thermal efficiency, where it is the ratio of desired output to the required input, the thermal efficiency here become as W net out over Q in, or can be written as Q in minus Q out over Q in. And this Q in minus Q out is actually come from the energy balance equation here. And this thermal efficiency equation can be simplified into this equation 1 minus QL over QH or 1 minus Q out over QH. And this QL is actually equal to or similar with Q out. Why? Because from this figure, we know that QL is the heat that released to the sink, which is Q out. And this QH is the heat absorbed by the boiler. L here stands for low temperature and H here stands for high temperature. So you can use both, either 1 minus Q out over Q in or 1 minus QL over QH. So now we have two equations, and these two equations are very important in order to solve any problem regarding heat engines. The energy balance equations and the thermal efficiency equation. Okay, now they have two figures here. On the left side, it shows us that some heat engines perform better than others, even though both heat engines are operating or absorbing same 100 kilojoule of heat from the same source. One of them can convert more of the heat they receive to work compared to the other one. For example, heat engine number 1, it converts 100 kilojoule of heat to 20 kilojoule of network output, compared to heat engine number 2 that convert 30 kilojoule of network output. So from here, we know that the thermal efficiency of heat engine number 1 is 20% and heat engine number 2 30%. For the right side of this figure, it shows us that even the most efficient heat engines reject almost one half of the energy they receive as waste heat. It shows us that most of the heat is rejected and we cannot convert all of the heat received to the work net out. It is impossible. Okay, next. They have a big question here. Can we save Q out? In a steam power plant, the condenser is the device where large quantities of waste heat is rejected to rivers, lakes, or the atmosphere. One may ask, can we not just take the condenser out of the plant and save all that waste energy? And the answer is unfortunately no, for the simple reason that without a heat rejection process in a condenser, the cycle cannot be completed. For example, this figure, we have a piston cylinder device with load. Initially, the temperature of the gas is 30 degrees C and it absorbs 100 kilojoule of heat from a reservoir at 100 degrees C. Then the gas expands, piston cylinder and the piston move upward, while the temperature of the gas increases to 90 degrees C. Since the piston moves upward, it means that the piston cylinder device does work, where the work output here is 15 kilojoule. Okay. Then the piston will move downward again in order to make a cycle. So here, in order to make a cycle or to make the piston move downward to its initial position, the remaining heat in the gas must be released to the surrounding. So now 85 kilojoule of heat must be released out in order to make a cycle. So from here we can conclude that every heat engine must waste some energy by transferring it to a low temperature reservoir in order to complete the cycle, even under idealized conditions. So without releasing any heat, a cycle cannot be completed. Okay, next, let's look at this example. Example number 1, a steam power plant produces 50 megawatt of net work while burning fuel to produce 150 megawatt of heat energy at a high temperature. Determine the cycle thermal efficiency and the heat rejected by the cycle to the surroundings. As I said in the previous slide, in order to solve the problem in heat engine, we have to remember energy balance equation and the thermal efficiency equation. From this example, we are given 50 megawatt, which is net work, and 150 megawatt, which is heat energy at high temperature. So therefore, from thermal efficiency equation, where the ratio is W net out over QH, we can simply change this W net out with 50 megawatt and the QH to 150 megawatt. Why? Because 150 megawatt is the heat energy that received to burn the fuel. That is required input, and 50 megawatt is desired output. They have terms here. Produce 50 megawatt of network. So from this statement, we know that 50 megawatt is the desired output. So therefore, the thermal efficiency is 33.3%. To answer the second question, the heat rejected by the cycle to the surroundings, we can apply the energy balance equation. Okay. From the energy balance equation of heat engine, we know that W net out is equal to Q net in. And the Q net in is Q in minus Q out, or QH minus QL. Therefore, QL here is the difference between 150 megawatt and 50 megawatt. And the final answer is 100 megawatt. Okay, next. In the second law of thermodynamics, they have two statements that we have to remember. And both statements are related with the devices that we are learn today. The first statement is Kelvin-Planck statement, and this statement is related with the heat engines. So what does Kelvin and Planck statement say? They say, or they conclude, that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce net amount of work. In a simple word, it is impossible for any device receive a heat and convert them 100% to net amount of work without having any heat waste. No heat engine can have a thermal efficiency of 100%. Or, as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. And the impossibility of having a 100% efficient heat engine is not due to the friction or other dissipative effects. It is a limitation that applies to both the idealized and the actual heat engines. And the statement of Kelvin-Planck can be shown in terms of this schematic diagram. It is impossible for any device operates on a cycle, receive heat from a single reservoir, one reservoir, and produce net amount of work without having any QL. This is impossible to be happen. Next, instead of heat engines, they have other mechanical devices that can be used to convert heat to work or work to heat. For example, is heat pump or refrigerators and air conditioners. So both devices can be used to convert heat to work or work to heat. Now let's look at the second device, which is refrigerators and also heat pumps. For the refrigerators and heat pumps, they are constructed by the four main components. The first component is condenser. Second is expansion valve. Third is evaporator. And last is compressor. And these refrigerators is used to transfer heat from a low temperature medium to a high temperature medium. Refrigerators, like heat engines, are cyclic devices. So they have an arrow here, which means the system operates on a cycle. The working fluid used in the refrigeration cycle is called a refrigerant, and the most frequently used refrigeration cycle is the vapor compression refrigeration cycle. In a household refrigerator, in our house, the freezer compartment where heat is absorbed by the refrigerant serves as the evaporator. Okay? So the freezer compartment inside our refrigerator is served as the evaporator. And the coils usually behind the refrigerator where heat is dissipated to the kitchen serve as the condenser. So if you stand at the back of our refrigerator, we feel hot due to the heat released from the condenser. Similar as heat engines, the refrigerator also have their own performance equation. For the refrigerator and heat pump, the efficiency is called coefficient of performance, and they are differentiated by the symbol of R and HP. R means refrigerator and HP is heat pumps, and the COP here is the coefficient of performance. The concept or the theory of the COP is actually similar with the heat pump. It is the ratio between desired output to the required input. For the refrigerator, the desired output is QL and the required input is W net. Why the desired output is QL? Let's look at this schematic diagram and look back to the meaning of the refrigerator. We know that the refrigerator is used to make the freezer compartment at low temperature as possible. The evaporator here is the compartment of freezer. So therefore, the desired input, the desired output is QL. We want to make the space at low temperature as possible. This is the objective of the refrigerator. So therefore, the desired output for COPR is QL. Then for the required input, it is W net in. The input that is needed in order to transfer heat from low temperature region to high temperature region, or the work needed to compress the refrigerant. For the heat pump, the desired output is QH. Why? Because the objective of heat pump is to warm up a space by absorbing heat from low temperature region. So we want to warm up the space. So therefore, this is our desired output. And the required input still W net in. The work needed to compress the refrigerant. Next, let's look at the COP again. We use coefficient of performance COP instead of efficiency for heat pumps and refrigerators. And this COP can be greater than 1 for the refrigerators, and it is always greater than 1 for heat pumps. And remember that for the heat engine, the thermal efficiency must be less than 1 and larger than 0. Or the thermal efficiency is in between 0 and 1 for the heat engines. For the refrigerator, can be greater than 1. And for the heat pumps, always greater than 1. Please remember this. Okay, now let's look again at the COP of refrigerators. The COPR means coefficient of performance for refrigerators, and it is equal to the desired output to the required input. And the desired output for the refrigerator is QL due to the objective of the refrigerators, which is to make the refrigerated space at low temperature as possible.